Hey everybody, Dr. A here, and in this video we're going to be providing some background information on how to compute the center of gravity, center of mass, or centroid of composite bodies. Now, in this video we're going to be referencing the Hibbeler Statics textbook published by Pearson. So if you have that book or any other statics textbook, you want to follow along and always use a good book to supplement whatever you're learning or whenever you're following videos like this one. So before we get started, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's dive into it.
Section 9.3, which is composite bodies, and this is computing the same values we discussed before: center of gravity, center of mass, and centroid of composite bodies. So what is a composite body? So a composite body is a body or system made up of several connected simple shapes. So when we say simple shapes, we're thinking like rectangles, squares, triangles, even circular segments. These are simple shapes. And we're going to say ... that we conveniently know the centroidal locations, okay, or the center of mass location or the center of gravity location. I think I spelled convenient. I'm not a very good speller. Conveniently. Okay, close enough, right? So what we do when we're evaluating these types of systems, these composite bodies, is we use the summation version of the formulation. Okay, so for example, for I'm going to say e.g. For centroid, we could say lines are going to be, you're going to have x bar equals summation x sub I L sub I divided by summation of L sub I, okay, as I goes from 1 to n. Okay, and then y bar equals summation of y sub I L sub I divided by summation L sub I goes from 1 to n. And then z bar equals summation z sub I L sub I over summation L sub I goes from 1 to n. Okay, so these are the summation versions of those integrals. And then, of course, we have areas and volumes. And, of course, we would have x bar for an area is summation I goes from 1 to n of x sub I a sub I divided by summation a sub I. And then y bar is summation I goes from 1 to n y sub I a sub I divided by summation a sub I goes from 1 to n. And then z bar equals summation I goes from 1 to n z sub I a sub I divided by summation a sub I. So I'm not going to write all of these out. I'm just going to say so on. And I'm also going to say same type of formulations for center of gravity and center of mass. So remember, the mathematical framework between center of gravity, center of mass, and centroid is all basically the same. They just physically represent different things, but they're mathematically the same. So the summation versions of all those integral equations are going to follow a similar pattern, okay? Now, a couple of simple shapes we want to keep in mind, okay? So when we look at centroid, we're going to talk about the following simple shapes, okay? Some simple shapes to consider, okay? If you have a rectangle or square, okay? A rectangle, oh, that's an ugly looking rectangle. A rectangle or a square, maybe with a base B and a height H, its centroid is going to be located right in the middle of those two dimensions. So it's going to be located at H over 2, and it's going to be located at B over 2, referenced from some origin, okay? Referenced from some origin. Triangle, then the centroidal location, we talked about this before. So let's say we got a triangle here. And it has a base dimension B and it has a height of H. And let's say this bottom left corner is our origin. So the centroidal location will be 1/3 of the dimension from the flat side of the triangle. So this would be like B over 3, and this is H over 3. So the centroid would be like right here, okay? So remember, for a triangle, it's always, the centroid's always located at 1/3 of the dimension from the flat side. So like here's a flat side, right? And then 1/3 of the dimension away from it is B over 3 in the horizontal direction. And then 1/3 of the dimension from the flat side in the vertical direction is H over 3. And then it's 2/3 from the point, okay? And it's in both directions. So the last piece we got to remember is if a reference axis slash origin is not given, then establish one.